Hello, welcome to MCX tutorial series. My name is Chen Feng. I am the author of MCX, Monte Carlo Extreme. If you are familiar with MCX, it is a GPU accelerated photon simulator, and it's used broadly in the biophotonics community to simulate light propagation inside complex media such as human tissues. By using the Monte Carlo method, it solves the radiative transfer equation and is accurate and also fast with GPU acceleration. Today, I would like to give you a tutorial on one of our latest tool that we developed called MCX Cloud. As if you're already used MCX, you know that MCX requires a graphics card to run Monte Carlo simulation, and particularly the NVIDIA graphics card, because it uses CUDA as a programming software. But many users may not have access to the latest and most up-to-date hardware, or even they have the hardware, there still requires some experience to optimize and install the hardware properly. So we developed MCX Cloud, and it is a cloud-based simulation platform. And a user does not need to have locally installed high-end GPU to run the simulation. It is web-based, and you can just log on our website and run simulation on a server that we maintain. Let's get started. To use MCX Cloud, you need to first go to our website, mcx.space. And on this is our main website, and you can find the download link for if you wanted to install MCX locally or use the cloud-based simulation. And to do that, you can go to the cloud link at the top of the first page. And that will lead you to a short description of this platform. And I will just click on this link to show you the actual interface. As you see, the MCX Cloud is a web-based simulation platform, and it has a simple interface. This is the main menu page. You can see a series of icons. Each icon corresponds to a module, and you can see the browse, and that is the tab that you can browse the user community submitted simulations or default simulations. You can go to the create button tab to fine tune and set the simulation settings, or use the JSON tab to view the detailed settings in the JSON format. And there's each of these modules correspond to a tab. To go back to the main menu, click on reset, and that will bring you back to the main menu. If you're not familiar with MCX, the best way to get started is to go to the browse menu and the browse tab. And the browse tab gives you access to the built-in examples, or in the future, users submitted simulations. In this tab, you can see there is a search box, and you can type in keywords if you have something that you have in mind, like bring simulation, and then you can type in the keywords and click on search. It will give you the result. If you do not know what to look for and wanted to see the default simulations, you can click on search, and that will load in the simulations in our library ranked by popularity. And by popularity, that means the most frequently downloaded and executed simulation will be ranked first. And in the future, depends on the user's needs, this order can dynamically change. And every time it loads in 5 simulations, and then you will load to the next set, just keep on clicking that button. After loading the library, you can see this, each simulation is designated as an icon, and that icon is a thumbnail of the 3D rendering of the simulation domain. And click on each of these thumbnail. It's going to bring you a detailed a tab on the right side and showing you what is the name of the simulation and some comments telling you the details, technical details of that simulation. You can click on each one of these to look at the background and what it's simulating for. Several simulations I would like to highlight. One is this MCX built-in example skin vessel, and this is created from Dr. Steve Jocks' MCXYZ software's benchmark. And this simulation consists of multiple layers with a vessel, a cylinder simulating the vessel. To load a selected simulation, you can click on this load button. And once you confirm, the simulation data corresponding to this, this example will be loaded to the JSON tab. And you can see that the settings are now loaded into the JSON tab. Similarly, this simulation will be rendered inside the preview tab. And you can use your cursor to rotate or zoom and to see the simulation setting. Because we use WebGL is a open standard to render 3D shapes inside the browser. This feature is portable across most modern browsers. You can currently we're using Chrome, but you can browse, do the rendering very quickly, efficiently, also in other many other browsers such as Firefox. You use the left button and to rotate, press and hold the left button to rotate the 3D object, and use the wheels to zoom in and zoom out. You can also press and hold the right button to translate the object across the field of view. Okay, so if you wanted to just run the simulation without any modification, you should click on the Run tab. And in this tab, we require you to fill in a very simple form. And this is mostly for our future reporting purposes for the NIH, which is National Institute of Health, funded this project. And these like your full name and your email and institute will not be public, and you will submit only to our servers, and it will not be made public. And if you choose, you can also have a network name, like your nickname that you use for your on the internet, and that can be in the future for attaching to the simulation that you submitted, or when you share it. So here I'm going to just type in my name and give you an example how to run the simulation. So once you type in these simple form, you don't need to register, but this is just all you need. And then you click on the submit button. So it will return from the server a hex key, and this key uniquely identifies this simulation. We call it a job ID. So the job ID is submitted to the server, and the server will execute the simulation. And because this is a built-in example, so we have a cached previously computed results stored on our server. So almost immediately you receive the simulation results back to your browser. And this is the simulation log printed by MCX when it runs the simulation. So when this is done, you can go back to the preview tab, and you can see the simulation results rendered as a 3D volume. And the color map, you can adjust it, the range of the color map by using these two sliding bars on the top. And for example, now if you wanted to render this and see what is a light propagation inside this complex medium, you can adjust the color map so to view it clearly. And this simulation contains again a 3-layer medium with a highly absorbing cylinder representing a vessel. And a disc-shaped source is placed at the bottom of the domain. And now you can see this is the fluence light intensity of the simulation in the 3D space. We use the maximum intensity projection to show you the whole simulation output. And you can see this from different views, and every view, the maximum intensity projection is computed and then displayed on this panel. If you want to download the simulation output, you can click on download output. So this will save the simulation output to your local disk, and you can use that simulation, for example, in the future to analyze locally. And I'm going to just click on this file, and then you can see this output is also a JSON-based file, and you can read it. It is human readable. That contains parameters, and then the simulation output that is encoded in this object. Now let's go back to the browse, and I'm going to give you another example. This one shows you how to create a simulation domain using shape primitives. And let me go to the JSON tab. This domain is, as I mentioned, made of 3 layers, and that layered object is defined by the Z layers construct inside the shapes object in the JSON input file. And I have 3 layers. Layer from voxel 1 to 20 in the Z direction is label 1. Medium between layers 21 to 32 is medium 4, and then so on. In the meantime, I also define a cylinder, and that cylinder is defined by the start point and end point in the axis, and then the radius, and this is assigned to a label of 2. So every medium in this construct from each one is identified by an integer. We call it the tag or label. And then you have to also define the corresponding optical properties in the domain object. And domain object has a subfield called media. And this media contains the values for the optical properties for each medium type. And the media object must have the same number of optical properties than the medium that you define in the domain. And it has also have to have an extra object as a first medium type designated as a background medium, and that is as label 0. This is the label 1, the absorption, scattering, anisotropy, and refractive index for the first label, and 2, and 3, and so on. So once you define the geometry and then define the optical properties, and you also need to define the source as what is the light launching from. The photons are being launched. This source is a disc-shaped source, and it has a center position and also a pointing towards the z-axis. This is the initial vector of the photon, and the radius of the disk is defined by this parameter. Once you define these simulations, then you can, basically you can see this input this domain setting by click on the draw last input button, and then the simulation results is then rendered. We can click on the last simulation. So this stores the last return simulation output, and this stores last submitted simulation input. Okay, so that is the one of the examples. I wanted to show you another example. For example, this is the calling 27 atlas, and this calling 27 atlas is defined by a voxelated domain. Let me load it. So once you load it, go to the preview tab. You can see there is a 3D volume made of the maximum intensity projection of this volumetric labeled domain. And you can see the background 0 is outside of the head, and then the scalp and skull is defined by, the scalp is defined by this label 1, and skull is label 2, and then you have CSF, and then gray matter and white matter. There's 6 labels, and then you have air pockets like the nasal cavities, and that's defined as label 6. There are a total of 6 tissue types, in addition with label 0 as air. And the source is located at this point and then pointing towards the center of the head. And these green dots represent detectors, and that they're also aligned on the surface, top surface of the head. Now, if you look at the JSON input file, and this is basically the text format description of the entire simulation domain, and that consists of the sessions section defines basic simulation settings. The forward field defines the time gates, the start and end simulation time gate, and the time gate width in seconds. These are basically 5 nanoseconds. In the opto section, it defines the sources where the photon is launched, and the detector, and where do you want it to capture the photons that escape from the simulation domain. And these are, in this case, we have a pencil beam and placed at this location, pointing in this direction. And the detector, there are 4 detectors, each one defined by the position as and a radius. In the shape field, and you can see that this domain is no longer defined by like cylinders or layered medium using those shape constructs. Instead, it's defined using a encoded field of a 3D volume, 3D integer array. And this is a single byte 3D array of this dimensions. And the data is then compressed and stored in this array zip data construct. So this particular format, we actually define it in an open standard called the JData specification. JData specification allows JSON to store, and this JSON is this text-based format, hierarchical data format, that typically is used for storing metadata, for example, some headers, data headers, etc. But traditionally, it does not have the capability to store binary and strongly typed data. And with the JData specification, we allow users to encode 3D binary arrays or high dimension arrays and other type of complex data structures inside JSON. If you're familiar, if you're interested in, you can go to our specification and look at the format. In any case, this construct defines a 3D volume of this size and this data type. and then it can basically be parsed and then provide this 3D array rendering. Now, if you wanted to run the simulation, I'm going to clear the previous simulation, and you can just go to the run tab and click submit. A new simulation will be submitted, but in this case, because in this preview version of MCX Cloud, we limit how many photons and also the domain size. So in this case, it cannot be submitted because of the preview restrictions. However, in the future, we will remove this restriction once our servers are all configured and optimized properly. Let me change my configuration so that you can see how to run the simulation. Okay, I have just temporarily disabled the limit check, and now you can simulate this large volume in the server. So to do that, just click on submit button, and you can see that another random job ID is also assigned. And on the server side, we have a script that runs every 20 seconds to check user submissions. If there's any user submission, and it will pick up, and then you can see that this is now start running. And once it completed, it will print the capture the MCX print log, and then return both the output as well as the log. And now we go to the preview tab. You can see this is the simulation output. You can see the simulation of light intensity across multiple layers of head. If you wanted to change the setting, you can either go to the JSON tab, and this is all in the human readable JSON format. It's all text-based. So if you wanted to change settings, for example, you want to change photon number to be, now it's 10 to the 6, you want to make 10 to the 7th photon. And once you change it, you can click on the update form, and then you can run it again. Similarly, if you do not want to edit this text file, then you can use the create tab, and the create tab provide users a graphical interface for editing each of the JSON fields. And for example, in the session, when we change the simulation photon numbers, we change it from 10 to the 6 to 10 to the 7, and this field is also updated. You can disable reflection, you can save other outputs, and all these are flags that you have probably have seen in MCX simulation input files. Each of these JSON field is mapped into one of these tabs, and you can edit the settings, the values, and once you change these settings, for example, let's just make this integer, and let's make this also integer. And once you edit here, and when you go to JSON tab, these fields are also synchronously updated. Okay, so once you change the setting, we change basically run 10 times more photons, or maybe 10 to the 8th. Again, in this preview version, we restrict simulation photon numbers to maximum 10 to the 7th, just for preventing some of the jobs holding all the GPUs, and we just try to limit the runtime of the simulation. But in the future, once the system is up and running, we will gradually remove these restrictions. I just show you how to use the Browse tab to load built-in examples or examples shared by other users, or using the Run tab to execute the simulation, and use a Preview tab to see the simulation results. Next, I want to show you how to create a simulation from scratch. Let's click on the Reset button to go back to the main interface. There are several ways to create a a simulation. And you can basically use there are two ways. One is by directly copy pasting a offline created JSON input file. And the other way is to create it using the Create tab. Let's start from this one because it has a graphical user interface to facilitate the simulation setting. The Create tab gives you access to 5 tabs corresponding to each one of the main structure in the JSON file, and you can basically use these graphical interface to adjust settings. And the Session tab gives you some basic information and overall settings for the simulation. For example, do you want to consider refractive index mismatch or not? Do you want to save the exiting photons on the outer surface? That's called the diffuse reflectance or diffuse transmittance, and other settings. You can use the Forward tab to define the start, end of the simulation, and also the time gate width in seconds. The Opto tab, you can specify the source type, direction, position, and direction, as well as other additional settings. You can also define detectors. Now, in the Domain tab, you can define what is a simulation volume and the optical properties of each of the tissue type or label. Now let's look at the default. There is a default configuration when you load in MCX Cloud. This is the default simulation. It's a 60 by 60 by 60 cube, millimeter cube, and each voxel is a 1 millimeter voxel, and filled with label 1. And the label 1, if you look at the optical properties, is basically air. 0 absorption, 0 scattering, anisotropy is 1, and refractive index is 1. So this is the default simulation. That's a trivial case. Basically, there's just completely filled with air, and the source is defined at the position at the middle of the bottom face at 30, XY, and pointing upwards. This is the Z, positive Z axis, and that's a pencil beam. So basically, it's represented by this arrow that pointing a source launched from here, pointing upwards. This is the default simulation. You can run it, but basically there's nothing. It's all zeros because there's no light energy deposition in this field. Now let's modify this just using the graphical interface. Let's go to the shape construct, and you see there's by default this creates a 60 by 60 by 60 domain filled with label 1. Let's keep it, and let's add a layered structure in the Z-axis. Let's create something called Z layers, and the Z layers are defined by a number of triplets, and each triplet define the start layer in Z voxel. This is voxel unit. So the what I define here is that I define a Z layer, Z-oriented Z-axis, a plane, a slab that is perpendicular to the Z-axis, starting at 20 millimeter, end at 40 millimeter, and filled with media label 2. So now you have 2 tissue types. 1 is everything in the cube. 2 is the layer between 20 and 40 in Z. So if you preview it, you can see that now I'm creating this new layer in the middle of the domain. Let's move the source to the side and tilt it a little bit. And let's go to the, to do that, you need to go to the Opto tab. And let's move it to along the y-axis and move it to the left side. And you can see that it's now pointing up, but move it to the left. But let's change the source type. Instead of a pencil beam, let's change to a slit source. A slit source is one of these types that's supported by one of the 16 or 15 source types supported by MCX. It defined a very thin sheet of light coming at a given position and a direction. So now the position of the slit, let's start from 20, 5, 0, and that is a position at the bottom of the plane. And the launch direction, let's make it tilted in the Y and Z direction. And this is square root of 2 divided by 2. And for the slit source, you need to define the length in each of the directions. In this case, I want to define 20 in X and 0 in Y as the length of the source. So the slit start from 25, 0 and moving in X direction by 20 millimeters, and no doesn't change in Y and Z. So if you preview it, you can see that my slit starting from 25, 0 and then moving, and then this slit will launch photons along this line. And the initial direction of the photons are all set as 45 degree from the bottom face. So this is the slit source. And then let's go back and we're done with the the source setting. And let's look at the optical properties. Now, since I defined tissue 2, that's inside the slab between 20 and 40. So let's add a third row, because the first row is labeled 0. This is the background medium. You always need to define this. This is medium type 1, and that's the medium inside the cube, outside of the slab. And then this is labeled 2, and that's medium type 2 that is in the slab. So let's give both of these a very small absorption so that we can save the fluence. And then let's leave the scattering unchanged. And this is basically non-scattering medium. And let's see what it looks like. Because of the slab is embedded in the middle of the cube, let's set it to a different refractive index. Let's make it 1.5 and see what is the sheet of light interacting with this slab. Okay, so now go back to the preview. You see this is still the same. You set this slit source pointing in this direction. You have a medium. Both of the background, this is tissue type 0, and this is tissue type, this is tissue type 1, and this is tissue type 2. Both of these medium are set to have no scattering. Okay, so let's see what is the distribution of light look like. Let's go to this run tab, and then you can type in the information, and then you can click on the submit button. And similar to the previous simulation, this is launched to the server and receive a job ID, a random key as a job ID. And then just a few seconds later, the simulated results are completed, and then the results are sent back to your browser. The simulation time you can see is only takes like 9 milliseconds. This is a very fast simulation for 10 to the 5th photon. Let's go to the preview tab, and we can see this is light distribution. So you launched the slit from here, and at this 45 degree, and then your beam of light is then refracted or reflected from this layer of slab, and that slab has a different refractive index. So the light is following the Fresnel's law, and then will be reflected and refracted, and then split again on the other interface. And then some of these beams keep on bouncing back and forth, and then created multiple reflections. Okay, so you can see this is the simulation going to give you non-scattering, basically photon simulations in this non-scattering multi-layered medium. Don't be fooled by the sort of low resolution look of this output. This is, you see these staircases is because this domain is rasterized with a 60 by 60 by 60 voxelated space. However, the photon retracing is done in the precise vector form. So each of the ray launched follow geometries of the ray in an exact angle and bouncing in this domain. And this output is only accumulated in the voxelated domain and show in low resolution. But these photon simulation ray tracing is performed in the floating point and accurate directions. Now, if you wanted to improve the smoothness of the simulation, you can also basically, you can just increase the voxel size, and that will also increase the simulation runtime as well. Okay, let's make some additional settings. If you want to, now this is one slab, you see the light split into several beams at the interface. What if we change the slab and make it 2 layers, and instead of 1 layer, let's go to the shape. So this is 1 Z layers, and now let's make 2. I'm going to add from 20 to 30, or let's say from 10 to 30, or 20 to 30, and 10 to 20, and 30 to 40. So we made a 2-layered medium, and let's put this also as tissue type 2, and let's preview what it looks like. Now you have a split the domain into by 2 slabs, and each of the slab is still non-scattering with a refractive index of 1.5. And let's run this simulation and see what it looks like. So once you submit the job, we have on the server a script runs every 20 seconds to pick up any new user submitted jobs. And so this is picked up almost immediately, and then the simulation is done in 10 milliseconds. Now let's look at the results. You can see that the 2 layers, 2 slabs, created even more complex reflection and refraction patterns. Okay, so basically you can simulate optical systems and with accurate physical following the light propagation physics and the probabilities like reflection and refraction are accurately computed using the proper statistical distribution. What if you create instead of using non-scattering, let's add a little bit scattering in those medium. Let's put layer 2 to have a little bit scattering, maybe 0.8 anisotropy. Let's see what it looks like. Let's also maybe increase the photon number. Now it's 10 to the 5th, 6 and 7s. Now let's run 100 times more photons and see what it looks like. Now this next job is, again, every time it get a random key, and then it first being queued in this in the server, and then a few seconds later, the script pick it up and start running. And now this is done. So this time it took longer, 500 milliseconds, complete 10 to the 7th photon. And then you can see the distribution. So now with the 2 layers now contains a little bit of scattering, you can see still the main beam, but the reflected beams back and forth are then scattered within these 2 layers, as well as the background medium. So you can see this is the distribution when you consider scattering in one of these 2 slabs. Okay, so basically you can go to either the create tab and each of these fields, and you can change it to, let's say I want to run a little bit longer, and then you can change the setting here. You can also consider, if you do not consider reflection, then basically you're going to see a straight beam going outside, but in this case you have to enable the reflection. And that is how you can create one simulation from scratch. The other way, let's go back to the main interface. The other way to create simulations from scratch is to import from your existing simulation. If you're already an MCX user, you probably know how to run an MCX from either the MATLAB interface or the command line interface. So I'm going to show you how do you do that. Basically, once you have the simulation in the form of a JSON file, you can basically copy paste the content into this tab. So let's start with the command line. So if you are familiar with MCX, MCX is basically an executable, and that you can use your own simulation input file, or you can use the built-in benchmark. And if you don't know which one to run, you can just use --bench. Then we're going to list what are the built-in examples, and then to see the JSON input file for each of these built-in example, you need to use give the name and use the --dump JSON flag. So this will output the JSON input file corresponding to this built-in example. It's called a spherical shells, and this spherical shells defines 3 concentric spheres inside a cube. So once you can dump the JSON input file, you can then copy paste this this data structure into the JSON tab, and then once you copy paste it, you need to click on the update form tab. So there are 2 things that are happening. One is the input JSON data file is being parsed and then reformatted. You can see that this is now reformatted in a nicer, cleaner look. Also, all the fields on this editor also updated. You can see now the input file that you typed in are also now displayed properly in each of the tabs on this create tab. Let's look at this imported simulation. So this is a multiple shells, and each shell corresponds to a label, and each label corresponds to an optical property. So you can see their tissue type 2, 3, and 4, up to 4 tissue types, and then you define this is type 0, type 1, 2, 3, and 4. So each one corresponds to a unique optical property. Okay, so then let's simulate this. Because every time I click on the reset button, it erases this typed information. But if you are stay in one session, you only need to type this once. Okay, so let's simulate it. If you submit a simulation and you think of something that you want to change, you can click on the cancel button. And this, once you click on that, it will become cancel. And then you click on again, the job will be canceled. If you realize something you want to change and don't want it to waste the simulation time, you can just cancel it before it picked up by the server. Let's launch it again and wait it to complete. So this one is also a very small simulation, so it's going to take just a few seconds to complete. So now it's when it says created, means the server start running that simulation. And when it's done, it prints, it says completed, and also give you the log. In this case, the simulation takes about 300 milliseconds on a 1080 GPU. Now let's look at the simulation results. So this is the simulation from the 3 spherical shell structure. So you can see that you can see roughly one of the shells is filled with CSF, like cerebral spinal fluid type of low scattering medium. So you see a increase of light intensity in this shell, and then you can rotate it from different angles. You can also change your settings by, for example, let's say I want to change outer sphere to make this to be a little bit bigger, maybe 28, and that if you preview it, you're gonna see I increase outer sphere. Again, this is filled with low scattering medium. Let's run this again. Now let's cancel this, and I will let's change the simulation photon number to, now it's 10 to the 6th. Let's change it to 10 to the 7th and run just a little bit more photons, and let's launch it again. Okay, so now I start running. Okay, done. So this time about 2 seconds to run the simulation on one of the 1080 GPU. So let's look at the simulation output, and this is this time is a little bit smoother because I used 10 times more photons, and you can clearly see that shell of light trapped inside this low scattering medium. Okay. So this is the you can export your existing simulation from built-in MCX built-in examples. If you wanted to go to one of your own simulation, for example, I'm going to use some external examples to give you another demo on how do you export from existing simulations. For example, I'm going to go to maybe this one. I'm not going to run it, but let me show you. So this one already have the JSON file, so you can basically use an editor, copy paste it, and then you can basically copy paste this and into this field. But what I'm going to show you is you can also use the dump JSON flag to create a new input file. And this input file has basically all the data that you typed in this simulation, and then you can copy paste this into this JSON tab, and then you can click on update. Now use this preview button. You can see that this is another Brain Atlas, and with a different, this is a full head structure, and a source is located on the top of the head. Okay, I'm not going to run this, but basically any existing simulations you can run that you can run from local folders, directories, and you can use the dash, give the input, give all the parameters, and then use dash dump JSON, and that will create the JSON file corresponding to your file-based inputs. If you have MATLAB, for example, you use MCXLAB to run simulations. I'm going to give you a quick example. How do you export simulation to run it in MCX Cloud? For example, I'm going to just use, so you go to MCX folder and go to the examples. I pick up this example from that demo. And as you know, the simulation, MCXLAB simulations are defined using a CFG data structure. And let's just run this and create that data structure. So this is the simulation run in MATLAB, and everything contains in this CFG struct. So to export this to a MCX Cloud simulation, you need to use MCX to JSON, and that you need to give the CFG and then give a file. You say this is 2D simulation. So this is going to export this file into a JSON file in this file name. And so I just open up this JSON file. This is the simulation that you exported from this CFG data structure. So now you can copy paste this data structure to here, and then you update form. Oh, there's something that doesn't accept. Okay, there's, yeah, the new line was causing the trouble. So now I can preview. So this is a thin object with a square shaped inclusion. So this is like a one thin object. Okay, so I just show you the basic usage of MCX Cloud, and hopefully it helps you get started. See you next time.